Everybody, we are on 9.9. We are almost done with our series, infinite series, Taylor series, all that stuff. Or we can move on and start learning some different things. Today we're learning about how to find a geometric power series and then use those and some other special properties to construct other power series that represent functions. Okay, so the first thing I want to do is review real quick what a geometric series look like. Okay, geometric series, we really wanted to start at 0. Otherwise, the summation formula doesn't work. And it was basically some constant times r to an exponent, right? So here's an example with some real numbers. It might be like 2 times 1/3 to the n power. And the cool thing about geometric series is we know that they converge if this number in here is less than 1. And we actually know what exactly they converge to. They converge to the constant that's on the outside divided by 1 minus 1/3, right? So we have that down here. Just the general formula for what a power series converges to is simply A divided by 1 minus R, right? Is assuming the absolute value of R is less than 1. Okay, and so what we're doing today is we're noticing that this kind of looks like this function 1 divided by the quantity 1 minus x, right? The difference is in here we had r, which is a constant. In our function we have x, which is a variable, right? So that x is going to change. And depending on what that x is, right, like we could determine if it was going to converge or not, right? We could find a radius of convergence. So what we're going to do right now is we're going to try to write a power series. Right, we're going to try to find a power series, just like we were doing last chapter, that represents 1 over 1 minus x, right? So we're going to try to write a infinite power series for this. So before we get to this step, we should show all the terms, and then we can write out the other thing. So the important thing about this is the fourth one that we're going to need to memorize. So far, I've talked to you about sine x, cosine x, and e to the x, and I've said that we need to memorize those. Like we need to memorize how to create that formula for those, right? So if you haven't got this down, like write this somewhere and start working on memorizing these, right? The way I like to memorize it is sine is an odd function, so it's all the odd ones that are going to come out of this, right? So we're going to get x plus, so that's x to the 1, which is odd, x to the 3rd over 3 factorial, and careful, we should get a minus sign there, plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. It's basically we could write the nth term for it, right? The nth term is going to be -1 to the, when we start, we get a positive, so n plus 1 times x to the 2n plus 1 over 2n plus 1 factorial, right? If I plug in 1 into that, we start at 0. If I plug in 0, I should get this guy. If I plug in 1, I should get that guy, and so on and so forth, right? And we can do the same thing for cosine. Cosine is even, so we get this. And we could write another similar nth term for that. And then e, like this is the part you want to memorize, is how to create it. E was just basically, you get all the terms in there, and it's never negative, right? It's just simply all of them together. You can just keep going, and it actually is the easiest one to write the formula for, right? It's just simply x to the n over n factorial is what e is, okay? So what we're going to do is we're going to create the power series for 1 over 1 minus x because we're interested in it because of the geometric series, right? So just again, a quick reminder, if you remember this part, just skip over it and we'll get to the new stuff in a second, right? A quick reminder of how we create the power series, right? The power series is created by finding f of 0, adding it to f prime, so this is the Maclaurin because we're centered at 0, plus f prime of 0 times x divided by, technically like 1 factorial, plus f double prime of 0, x squared over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial, basically plus dot 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 f to the n of 0 over n factorial times x to the n, right? That's how we create this. So that's what we're going to do for f of x here. So as you can see, basically we need a bunch of derivatives, right? We need the first few derivatives, however many terms we want. We just want to do this until we see a pattern. So let's go ahead and find the first derivative, which is going to require quotient rule, right? There's a u and there's a v. So u prime v minus v prime u prime is 0 times anything is 0, so we don't need to write the rest, minus v prime, the derivative of this bottom piece is negative 1 times 1 all over 1 minus x quantity squared, which simplified just gives us 1 over 1 minus x quantity squared. And then we're going to find the second derivative, which derivative at the top is still 0. 0 minus derivative of this piece is 2, 1 minus x to the 1 times 1 over 1 minus x quantity to the 4th power now. And maybe what you can see here is that this 1 minus x is going to cancel one of the 1 minus x's down here, which makes that a 3, and we're left with negative 2. Sorry, when I did this, there should have been a negative 1 coming out of this, because when you take the chain rule derivative of the inside, you get a negative 1, which changes this to positive, because you have a negative times a positive, negative times a negative. And we have 1 minus x to the 3rd down here. F triple prime, let's stop it. Let's stop after 3, because we should be able to see the pattern after this maybe. If not, we'll do another one. Is the derivative of this guy, which derivative of 2 is 0. So 0 minus the derivative of this is 3 times 1 minus x squared times negative 1. That's what I missed last time, right? We're taking the derivative of the inside, gives us negative 1. All divided by 1 minus x to the 6th power, right? That's 1 minus x cubed raised to the 2nd power. Maybe you can notice here that these two are going to cancel 2 of those, and we're going to get a 4 right there, right? So we're going to get 3. Oh, and I also missed something else, right? I missed multiplying by u, so there should be a 2 right here as well. So we're going to get 6 over 1 minus x to the 4th. I don't know if you see the pattern, but maybe you can see this is 1 factorial, this is 2 factorial, this is 3 factorial. Can you guess what the next one's going to be? 4 factorial divided by 1 minus x to the, let's see, 2, 3, 4, 5. Yeah. And then, so the nth term would just be n factorial over 1 minus x to the, this was the 4th derivative, but it gave me 5 there, so this would be like n plus 1. It's always 1 more than what it says. So now we're ready to do this, right? So our p of x is going to equal f of 0. If I plug in 0 to this, I get 1, so 1, plus if I plug in 0 to this one, we get 1 over 1 minus 0, which is also 1. So this would be plus 1x, right? That's coming from there. Plus the second derivative times x squared. Let's go ahead and put the x squared here. X squared over 2 factorial. In this case, if I plug in 1, I'm going to get 2. Right? So we put the 2 up there. If I plug in 1 to the third derivative, we're going to get 6. So for the third derivative, we have 6 times x to the third over 3 factorial. But remember, 3 factorial is 6, right? So like these are going to cancel. Those are going to cancel. And basically, when I do f to the, like the nth thing here, we're going to get n factorial, right? We're going to get n factorial over 1 when we plug in 0. So this like the nth term in this one is going to look like this, right? I'm looking at this and saying, well, the nth derivative is going to be n factorial divided by n factorial. So the nth term is just x to the n, right? So this is another one to remember, right? It's even easier than the e, right? It's just 1 plus x squared, right? So if we simplify, it's just 1 plus x squared plus x to the third plus x to the fourth plus ... plus x to the n, right? So it actually turns out to be a really nice one, right? Where you can just add all the x's and increase the power a little bit every time. So what we need to do is check for, and we could go through the whole thing and show when it converges. We're kind of running out of space, but remember where it came from, right? It came from when this number r was less than 1, right? That's when the geometric series converged. But in this case, the r is just x, so this will converge when x is less than 1, which you could show that using the ratio test, but you can kind of also reason through it in this case. So like this converges when the absolute value of x is less than 1. All right, so what we're going to do is we're going to try to use this thing that came from the geometric series to create some other type of power series that are centered at 0 at this point. And then we'll talk about how to center it at a different number later on. So here we are, example number 1. We're trying to find a geometric power series for this guy, 4 over x plus 2. What we want to do is we want to write it in the form like this, where it's a over 1 minus r, so that we can see how to use that other series to create it, right? So in this case, let's go to start by writing it as 4 over 2 plus x, right? So we need this 2 to be a 1, right? And we need this plus sign to be a negative sign, right? So what we're going to do is we're basically going to factor out a negative 2 from the denominator, right? We're going to factor a negative 2, which is going to leave us with, oh no, sorry, that's not factored a negative 2, because I need the 1 to be positive 2, right? I need it to be positive 1, not negative 1. So we're going to factor out a 2, and that's going to give us 1 plus x over 2, right? And then what we're going to see is that this 4 and that 2 cancel a little bit, so now I have a 2 in the numerator, and I need a negative sign right here, right? But I have a positive sign. So we can just write a double negative, right? We can write 1 minus negative x over 2, right? And what this allows us to do is see that this is that r value, and this is that a value, right? So it took some manipulation to get it into this form, but we can see that it looks like that now, right? We can see our a, we can see our r. And so what this allows us to do is write this in the form, oh, sorry. Okay, so we're going to use the thing that we already created and just ask ourselves, well, how is this different from that, right? Well, this one has a 2 out here, which means there's basically a 2 multiplying the entire thing, right? And then how else is it different? Well, instead of x, we have negative x over 2, right? So everywhere I see an x, I'm going to put negative x over 2, right? We're just we're doing that thing we learned last time in the last section. So this is going to be 1 plus negative x over 2 plus negative x over 2 squared plus negative x over 3 to the third power plus over 3, x over 2 plus, I don't know how far we need to go, negative x over 2 to the fourth, right? We're just replacing all these x's with negative x over 2. And then we could simplify this. And we would write, I think it's easiest to keep that 2 on the outside, but we just maybe rewrite this a little bit like such. And you can see that this one now alternates a little bit. If we wanted to write the nth term summation for it, it's actually kind of easy if you just know the a and the r right? And we know we're writing a geometric series, so in this case a is this and r is negative x over 2. And remember that a geometric series looks like this. Then we can just put like that, right? And that's like the nth term. So that's that. We also would want to talk about where it converges, right? Like where is this going to converge? So we know like the original, this one converged when absolute value of x was less than 1. Well, this one again, it's kind of just like you're replacing the x with the new thing, right? So this is going to converge when negative x over 2 is less than 1, right? That's just that same thing that we replaced all the x's with. We just replaced this x with it as well, right? So again, we don't want to leave it like this because we want to be able to see our radius of convergence. So we really should multiply both sides by 2, which would give us and the absolute value of a negative, like the negative is unimportant inside, so it's just going to be x, absolute value of x is less than 2, right? So the radius of convergence is 2, right? The radius of convergence is 2. The interval of convergence, since we're centered at 0, is going to be from negative 2 to 2. We should check the endpoints, which let me think about this. No, we can't check the endpoints in this. Think about if I plug in negative 2 up here. We would get an undefined thing, right? So that wouldn't work. And if I plug in 2, I get 1, which would be a divergent geometric series, right? Like if I plug in a negative, if I plug in, either way I'm going to get a number greater than 1 here. So like the endpoints don't converge because they're the ones that give me a 1 on the inside of this, right? If I plug in negative 2 and 2 there, I'll get either negative 1 or positive 1. Either way, that makes r, the r in the geometric series greater than 1, and so it diverges. So the interval of convergence would be negative 2 to 2, not including the endpoints, because the endpoints make the series diverge. All right, so here's another example. We're going to find another geometric power series, meaning we're using this same idea up here. We want to write it so it looks like our a over 1 minus r. Again, the a is just a number multiplying on the outside. Again, in this case, that's 1. In this case, we have 1 over x, which we need like a 1 minus something, right? We want it to be a minus sign here. So what we can do is a little trick where we add 1 and subtract 1. So basically add 0, right? So we're going to add 1. And I'm going to subtract 1. Basically, I just added 0, right? 1 plus negative 1 is 0. So I didn't change this because I can add 0. It doesn't change anything, right? Now we're going to go to rewrite this a little bit. Remember, we need 1 minus this thing. So we're going to do 1 over, again, we're going to do minus a negative. And we need this to be negative when we distribute that negative, so it has to look like that. And now you can see that it's in that form, right? The a is up here and the r is that. Right? A is 1 and r is negative x plus 1. So what we can do is we can write if f of x equals 1 over x, we can write an infinite series from 0 to infinity. Again, we already know what a is, so it's going to be 1 times negative x plus 1 to the nth power, right? Again, we're just writing a and r according to this, and that's the placement that's in here. And then we're going to write out our sequence. Again, we can just go back to this one that we should memorize, right? This one here. And we're replacing all of our x's with negative x plus 1, right? So it's going to be 1, because there's no x, plus negative x plus 1, plus negative x plus 1 squared, plus negative x plus 1 to the third, plus dot 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 basically just negative x plus 1 to the nth power, and we just keep adding and it'll be equal. And again, we could just kind of clean this up, right, if we wanted to. Actually, you know, the only real cleanup that this one has is you can write it like I mean, we could write negative x plus 1 like this, and then the rest don't really change, so I guess you could have a 2 in the front, but that's not a big deal. So when does this converge? Well, this converges when negative x, the absolute value of negative s plus 1 is less than 1. And so our interval of convergence, our radius of a convergence is still 1, right? Our radius is 1. Our interval of convergence is a little harder to see here. Usually it's just this number, but this is negative x plus 1. So maybe in this case it's actually good to like solve it, right? So we're just gonna solve this the way we did in Algebra 1, right? We're gonna write two separate equations. Right, and the only thing that changes is in one of them you flip the inequality symbol and make the other one negative. And so solving this is going to give us x is greater than 0. Solving this one is going to give me x is less than 2. Right, so if I graph that on a number line, there's 2, there's 0. We're talking about this space. And again, for these ones, the endpoints are not going to converge because those are the ones that make that radius 1. Right, so my interval of convergence is 0 to 2. Right, interval of convergence. All right, so there are some operations we can do with power series. Basically, it's the same operations we've been doing for a really long time. If you multiply the inside by a constant, it basically creates this thing there, right? If I raise the inside to the nth power, it basically multiplies the exponent here. And if I'm adding two functions like such, then I can basically just add the coefficients that would create each of those, because right, this f of n is that and g of n is that, so I'm just adding the nth term piece for f to the nth term piece for g. It's kind of like not the obvious ones, but the ones we would expect to see. All right, so our goal now is to figure out how do I apply that to things like this to create a nice power series for these. Oh, before we move on, I should mention that when we do these operations, it does change the interval of convergence, and it kind of depends how it changes it. So just be careful, like your interval of convergence won't remain the same. You'll have to double check what that is. Okay, so here we are. We're trying to find a power series centered at 0 for this thing. When you look at this, you'll probably start seeing that there's some, whenever we see something like this, it's going to end up being that thing that most of us don't like, but it's partial fraction decomposition. So the first thing we want to do is factor this denominator. It's going to be x plus 1 and x minus 1. Right, and we basically what we're going to try to end up using is this third property here, where if we can write this as a sum of two things, then we can figure out like a single series to write it as, right? So what we're trying to do here is we're trying to separate this into two separate fractions. We don't know what the top number is, right? And the denominators here are the same as the things that were there. Basic idea is, well, what did we used to have before we found a common denominator? So we're just going to ask, like, what are this a and the b before we had a common denominator? Basically, it just requires us to find a common denominator. So we're going to multiply this one by the denominator of the other one. And we're going to multiply this one times x plus 1, which is the denominator of the first one. And we're going to get, a times x minus 1 plus b times x plus 1, right? I just wrote this and that down there. And because they have a common denominator, like when we add them, the common denominator will stick, right? So we're down to that. These two things multiplied, right? That's just these guys here. And then what we need to do is figure out, we need to arrange all the x pieces together and all the non-x pieces together, and then figure out what the coefficients are so they equal this. So this is going to require us to actually distribute. We're going to get ax minus a plus bx plus b. I'm just going to do the top real quick. So the denominator is still there, but we need to just work with the top for a second. Okay, we're going to put all the terms with a x in it. So ax plus bx minus a plus b, right? So all I'm doing is taking this and writing it there, this and writing it there. This guy got written there, and this guy got written there, right? And then the last thing we're going to do is we're going to factor out the x. So we're going to have a plus b times x, right? I'm factoring it on the right-hand side just because it's a little bit easier to see. And then a plus b. And now I'm going to go and put that denominator back down in here. It was there the whole time. I just didn't want to write it that many times, right? And what we're saying is this has to equal 3x minus 1 over x plus 1, x minus 1. Okay, so the denominators are the same. This piece right here is the coefficient of x. I need the coefficient of x to be 3. So I can write a plus b equals 3. Or maybe it's better for you if I write it as 3 has to equal a plus b. And then I can see here that the constant piece is these two, needs to equal -1. So we're going to write -1 equals -a plus b. And this is a system of equations, which in this case is really nice. You can solve using elimination. You just add straight down. Those are going to cancel. We're going to get 2b. And we have 2 equals 2b. We divide both sides by 2. And we get b equals 1. And if I know b is 1, then I can just go up to maybe this equation, right? I know that 3 equals a plus b. Well, b is 1. So 3 equals a plus 1. A must be 2. Right? So now I know for this original thing that I had written over here, I know what a and b are, right? So I can write that 3x minus 1 over x squared minus 1 is actually equal to a over x plus 1, where a is 2. So 2 over x plus 1 plus b, which was 1 over x minus 1. And now I have two little separate fractions, which I can work with to write in the geometric form, right? So I want to rewrite each of these so they're in the form of a over 1 minus r. All right, so the first thing let's do is let's go ahead and write them as with the x over on the right hand side and make it a little bit easier. All right, so I need the first number to be a 1, fine. On the first one, that's fine, but I need it to say minus r. I need a minus sign there. So we're going to write 2 over 1 minus negative x, right? And then in the second one, I don't want a negative here, right? So I want to write like a factor of negative out, and that would make it 1 minus x. And, you know, instead of having this negative down here, we can go and just kind of like bring it up there, right? Like that happens. And then we have this, which is the same as that, right? 1 minus that. So in the first one, a is 2 and r is negative x. And in the second one, a is -1 and r is just x, right? Because it's 1 minus r. So r is just x in that case. And so we can write two separate geometric power series for this. We don't need to write out all the terms. We can just write the little summation thing. N is 0 to infinity. A is 2 for the first one, so 2 times negative x to the n. And we're going to add that to the second one, which is still goes 0 to infinity. In this case, a is -1 times x to the n. All right, and we can clean this up a little bit. Since it's negative in here, we could just bring that out as negative 1 to the n power times 2 times x to the n, plus the second one is still negative 1 x to the n. The reason we want to do that is we wanted to get our x pieces to be identical. Otherwise, negative x is not the same as the other one. And then we're going to go back up here and we're going to use this guy, right? Where I can just add the terms for, like basically this is f, this is my representation for x, and this is my representation for g. And so I can just write this as, the x to the n is similar. You can kind of think about it as factoring on x to the n. And in here, I'm just going to put the two things. I'll put this plus this, right? So negative 1 to the n times 2 plus negative 1. And that's like the nth term piece of it. If you wanted to write it out, you just start plugging in numbers, right? So you plug in 0, you're going to get 1, 2, 1, you're going to get 1. If you plug in 2, you're going to get a negative number. Wait a second. If you plug in 2, you just get 2 minus 1. Sorry, I don't know why I'm plugging in 2. I should be plugging in 1 right now, right? I plugged in 0 before. Now I'm plugging in 1. If I plug in 1, I get negative times 2, which is negative 2, plus negative 1 is negative 3 times x to the 1, right? And then if I plug in 2, now I'm getting a positive times 2 minus 1, which is 1, and then x to the third. And then if I plug in, I plugged in 2. If I plug in 3, I should be getting a negative again, right? Negative 1 to the third power. It's going to be negative. And then I get 3 again, x to the third. You can see the pattern. All the even ones are going to have 1, and all the odd ones are going to have a 3 and be negative, and so on and so forth. All right. So I know that's really long and crazy. We should talk about the interval of convergence, right? Since they're both, we just have to figure out, since it's a geometric series, right? We need to make sure this is our r, has to be less than 1. So again, the radius of convergence is just simply the absolute value of x must be less than 1. So r equals 1, and the interval of convergence is just going to be from negative 1 to 1. All right, let's do some other examples. Okay, so this one's asking us to find a power series for f of x equals natural log x. And we could go through the whole process of take the derivative and use that power series formula. We have the derivative times x minus 1 to the nth power over n factorial. The cool thing is, if you remember from example 2, we looked at the function 1 over x, and it was centered at 1, and we had this infinite series that described it. Right? We'll go back to the example in a second. That was negative 1 to the n. Let's go back to that example 2. It's here, so negative x plus 1 to the n power. So let me erase this. Negative x plus 1 to the n power, like such. And we remembered last chapter that we could integrate and differentiate, and our interval or our radius of convergence wouldn't change. but the interval might, the endpoints might. So the question is, well, what if we integrate that, right? What if we integrate both sides of this, right? Isn't the integral of 1 over x just natural log x, right? So like without having to do all that extra work, we're finding the series for natural log of x, right? So if we integrate this, we're going to get, we'll use the rule for integration, -1, negative x plus 1 to the n plus 1 divided by n plus 1. There is a little factor of a negative being in here, so really we have to put a negative out here. And then don't forget plus some constant, right? Since it's centered at 1, we can plug in 1 to find out the value of c, right? So if you let x equals 1, you're going to get 0, right? So basically, by doing that, by letting x equal 1, we see that c will equal 0, right? So this c is just going to be 0 in this case. So we should write it, but it's not there. So we can find out that natural log x is actually equal to this thing here. Oh, I should have the summation out here. And if we wanted to find some of those terms, we just start plugging in numbers, plug in 0, we're going to get negative, right? It's going to be negative. This is going to be 1 over 1. So it's going to be -1. No, sorry, I plug in 0, there's still a 1 power, so it's negative x plus 1 to the first power, because I plug in here, I still have an exponent of 1 over 1. And then I plug in 1, and we get 2 up here, right? 2 in the exponent, 2 up here, and 2 on the bottom. So it's going to be plus negative x plus 1 squared over 2. And then minus negative x plus 1 to the third over 3, and so on and so forth. Right, we have to plug in we're plugging these into the n values, right? That's what I was kind of messing up on in the beginning. And so we have a series that describes natural log of x. All right, let's keep going. So we want to find a power series for g of x equals arctan, centered at 0. Now, this may seem weird, but remember, just like, do we remember some other thing for arctan, right? Do we remember that if we had g prime of x, sorry, somebody's knocking on my door. And just if we remember, like, if we took the derivative of arctan, right, or if, I don't know if we need to write this, but the derivative of arctan, or tan inverse, is 1 over 1 plus x squared. And they really seem to like arctan, so I'd definitely encourage you to remember this one, right? And then, so if you look at this, like, this looks similar to the thing we've been working on, right? It's basically the same thing as our, if f of x, if our original thing was this 1 over 1 minus x. Hold on one second, I'm trying to verify something here. Okay, so we're gonna start with this. We're gonna start with our goal is to get it in a over 1 minus r form, right? But we're gonna go and start with this and show what this one is. Okay, so if this one is gonna be, if I write it in that form, it's gonna be 1 over 1 minus negative x, right? Which in this case a is 1 and r is negative x. So this is going to give us the infinite series, the infinite powered geometric series of 1 times negative x to the n, right? Which can also be written as, instead of a negative on the inside, we could, like, just like negative 1, right? We could write it as negative 1 to the n times x to the n, right? So we're going to write it that way. We're going to write it negative 1 to the n times x to the n, right? So we're showing that this is equal to this guy. And then if we're trying to find this arctan thing, it's 1 over 1 plus x squared, right? It's basically just this f of x function that we had, except we're going to, instead of having x, we're going to have x squared. So we're going to take this formula we had here, which was for 1 over 1 plus x, and we're going to replace everything that has an x with x squared, right? So it's going to give us, this stays the same. We're going to replace our x with x squared, right? And this is going to give us negative 1 to the n. You multiply powers when they're raised like this, right? So it's going to be x to the 2n power. And so this is the infinite series that represents 1 over 1 plus x squared, right? And so what we can do is, if we integrated this, right? If we integrate this series, then we will have arctan, right? Because if we integrate 1 over 1 plus x squared, we'll have arctan. So by doing this, we're going to come up with an infinite series that represents arctan, right? So let's go to integrate. Again, integrating is just applying your power rule, right? This guy is say the same because it's a constant. We are going to add 1 and divide by whatever we get, like such. And then don't forget you have a plus c, right? So we're saying arctan, let's just do tan inverse, it's easier to write, is that. And we should find the value of c. So if we let x equal 0, then we can see that c will also equal 0. Right? Plug in 0 for x, you're going to get 0. And we could write out, so that this is the formula, this is the thing for arctan. If we wanted to write out the first few terms to actually try to approximate it or something, we just start plugging in numbers. Plug in 0, it's going to be positive x to the 1 over 1. If I plug in 1, it's going to be negative x to the 3 over 3. Plug in 2, it's going to be positive x to the 5 over 5 plus so on and so forth, right? The interval of convergence, because we started with that geometric series, it's still in that. It's the interval of convergence is still negative 1 to 1, right? The radius is 1. The interval of convergence is negative 1 to 1. All right, so I think that's it for this. I wanted to show you one challenge problem. It doesn't really have to do with this particular subject, but I don't know if you guys remember seeing my bottle in the class that I always drink out of. It actually has a pretty applicable problem on it. So I challenge you to figure out the sum of this this series right here. Right, it's a little bit different because it's it's going to n, but like just maybe imagine this is n and all these things are n, and then have it go to infinity, and see if you can figure out what it goes to. See if you can figure out what it converges to, or if it converges at all. Right, it's a challenge for you. If you figure it out, let me know, because when I figured it out, I was drinking out of the bottle for like a year, and I didn't know what it was. And then one day I got bored. I think it was over the summer, and I did it, and I was like, wow, that's been on my bottle this whole time. So cool. All right. Have a good one.